Ever wonder how self-driving cars avoid crashes, follow traffic rules, and still drive smoothly? It's not just about speed or sensors, it's about constraints. These are the invisible rules that keep vehicles safe, efficient, and human-like. Today, we're diving into a cutting-edge framework called Drive that uses smart math to handle these constraints, making autonomous driving smarter than ever. Let's start with the basics. Imagine programming a robot to drive. You need it to obey rules like don't hit other cars, stay within speed limits, and don't swerve unpredictably. But some rules are easy to write, like speed limits, while others, like avoiding sudden obstacles or mimicking how humans drive, are tricky. That's where Drive comes in. It uses two types of constraints. Hard constraints, non-negotiable rules like not crashing, and soft constraints, flexible rules like staying close to human driving patterns. Here's how it works. For hard constraints, Drive uses mathematical optimization to enforce strict limits. For example, it ensures the car doesn't exceed the speed limit or get too close to other vehicles. But for soft constraints, like avoiding unexpected obstacles or mimicking human behavior, it employs a technique called inverse constraint learning, ICL. Instead of hard-coding these rules, the system learns them from real-world driving data. Think of it like a student learning from a teacher's examples rather than a textbook. Now let's break down the math. Drive optimizes multiple goals simultaneously. It minimizes travel time, reduces energy use, and prioritizes passenger comfort by smoothing out jerky movements. But how does it balance these competing objectives? By using a convex planner, a mathematical tool that finds the best path while respecting all constraints. This is like a GPS that not only avoids traffic jams, but also checks for road closures, speed limits, and even the driver's preferred routes, all in real time. The real test. How well does Drive perform compared to other systems? Researchers tested it on real-world driving data from highways, intersections, and more. They measured violations of rules, lower is better, driving smoothness and decision-making speed. The results? Drive outperformed other methods by a significant margin. It had 0 violations for soft constraints, stayed closer to human-like driving patterns, and even handled unpredictable obstacles without explicit programming. But here's the kicker. Drive doesn't just follow rules, it learns them. By analyzing millions of driving scenarios, it adapts to new situations, like sudden lane changes or unexpected pedestrians. This makes it not just safe, but intelligent. Now let's see how this plays out in real-world testing. Take the round D01 dataset, where navigating a roundabout feels like a game of bumper cars. The algorithm's first guess for a path. A disaster. It's like trying to plan a route in a chaotic environment. Every move risks a collision. The system had to retry repeatedly, leading to the highest failure rate. Tight turns and low speeds. They're a recipe for digital panic. Then there's high D01, where constraints were too strict. Overtaking was nearly impossible. If the car in front stopped even a meter too far, our self-driving car couldn't move. It's like being stuck in traffic with no lanes to switch into. No matter how hard you try, you're stuck. These constraints kept things safe, but made the car too cautious. But not all tests ended in frustration. In the ND01 dataset, things worked surprisingly well. One car turned right so smoothly, it felt like a human driver. The system calculated 133 steps to avoid collisions while keeping the ride comfortable. Another test. A massive roundabout maneuver with 487 precise steps. It was like watching a ballet of math and physics. Here's the cool part, the system learned. Early on, its paths were all over the place, like a beginner driver zigzagging through traffic. But by the 100th training cycle, it was smoothly following lanes, respecting speed limits and dodging obstacles. It's like watching a student driver grow into a pro. So what does this mean for real-world self-driving tech? These constraints are lifesavers, they prevent crashes. But they're a double-edged sword. Too strict and the car gets stuck. Too lenient and risks rise. The key: finding that sweet spot where safety and efficiency dance together. Next time you see a self-driving car, remember, it's not just about speed or smarts. It's about mastering the delicate balance of rules, physics, and real-world chaos. Thanks for watching. Hit subscribe for more deep dives into the science behind the tech.